So in the electron transport chain, electrons that moved from complex 1 into the ubiquinone pool to complex 3, electrons that moved from succinate into complex 2, also to the ubiquinone pool to complex 3, are now gone to cytochrome C, where they're going to wind up in complex 4. These electrons are then going to be used to reduce oxygen to water. As they catalyze oxidation reactions, the complexes 1, 3, and 4 are also going to be pumping protons across the mitochondrial membrane to give us that proton gradient. So do note and remember that complex 2 doesn't actually do any proton pumping. So cytochrome C is a mobile electron carrier. So it is soluble in water. It's going to go through the matrix and carry electrons from complex 3 to complex 4. There's a heme in the complex of the cytochrome C, which is covalently linked to the protein via 2 sulfur atoms. Now on to complex 4. This is going to be cytochrome C oxidase. So yes, this is named for the fact that it's going to be able to oxidize cytochrome C. The electrons from cytochrome C are going to be used in a 4-electron reduction of oxygen to produce 2 waters. We'll take a closer look at that reaction down at the bottom. Oxygen is going to be the terminal electron acceptor for the electrons in the electron transport pathway. So at the very end of the day, after everything happens, oxygen is where everything winds up. It all ends with oxygen, which then is reduced to make water. So that cytochrome C oxidase is going to utilize 2 hemes, A and A3, and 2 copper sites. The complex 4 is going to be transporting protons across the inner mitochondrial membrane. So you're going to have 4 protons participating in oxygen reduction, and then 4 more are going to be transported in each catalytic cycle. So overall, we are going to have the oxidation of the heme group in cytochrome C. So that's where you see that iron 2 going to iron 3. Then because what we're doing is looking at the reduction of oxygen, in the reduction of oxygen to make the equation balance out, that is going to be making 1 whole oxygen molecule go to 2 waters. So then as we look at this, it is going to take cytochrome C multiple trips. So it's going to take multiple molecules of cytochrome C in order to make this reaction work. But what is going to happen then is this is all shown then in a half reaction. What we were looking at previously was looking at a balanced reaction. So we were looking at a whole oxygen going to 2 waters. Now as we look at this slide, this is showing a single reaction where you're going to 1 water. So you'll notice that some of the numbers here are a bit off because now we're talking about only using half of a molecular oxygen molecule or 1 atom of oxygen to go to 1 water molecule. So for this setup is why you then see 2 cytochrome Cs, but those electrons from cytochrome C are going to move to copper, which are then going to move to the cytochromes, the hemes that are then inside that complex 4, which then will go to reducing oxygen. So again, the big picture here is to just make sure that you remember that oxygen is going to be the last electron acceptor in all of this. So we're reducing oxygen as that last step. Do keep in mind the numbers in here, but just watch the numbers and make sure you're watching if you're talking about a whole molecule of oxygen or half of that molecule of oxygen, and that'll help you with what's going on with all the numbers of different things on the different slides. So its structure, this is also relatively large, lots of alpha helices, and again, this is going to involve things that are across the membrane. So complex 4 is still membrane embedded. So by now, we've actually talked through all 4 of the complexes, including that little bit on cytochrome C. So whenever we're dealing with mammals, remember we are going to be looking at 4 protons being pumped by complex 1. A total of 4 protons get exchanged into the inner membrane space from complex 3. 4 of those are from ubiquinone, and then the 2 that you see going in are from that other bit of ubiquinone going to ubiquinol in the Q cycle. Complex 2 is not going to contribute to any of the protons being pumped. It does contribute to the ubiquinone pool, so yes, you can always make the argument that it helps, but for the sake of simplicity, since complex 2 doesn't actually involve any protons, we're going to leave that one out of it. And then your complex 4 is also going to have the pumping of protons. So again, you see those 2 protons pumping. That's because we are reflecting on the fact that we're producing that 1 molecule of water from half of a molecule of oxygen. And again, remember that throughout this entire pathway, what you see is the transfer of electrons continually going to things that are more easily reduced. That is, every time we're making a move in electrons, you're moving the electrons to something that has a more positive standard reduction potential. E. coli are different. So E. coli still do have electron transport chains. They still do have ATP synthases, but they're different. E. coli don't have organelles, so they're not going to have mitochondria. Instead, they're going to pump protons just out of their cell membrane and then have things rush back in. So in order to do this, they have an NADH dehydrogenase, so that part's the same, and then they have a quinol oxidase. So they're still going to use that coenzyme Q as an electron carrier. But overall, this is a lot simpler. But notice that they're still starting with NADH. They're still ending with oxygen as a terminal electron acceptor. So they are still using a lot of the pieces. It's just a much simpler electron transport chain overall. So if we were going to take a look at this, again, basically there's two main complexes involved in this. One's that NADH hydrogenase. The other is that quinol oxidase. You have a ubiquinone pool then that goes in between them, and these are then also going to be pumping protons. Notice that you're not going to get nearly as many as you get in the eukaryotic electron transport chain, but you do get a total of 6 going on, so it still is enough to have the E. coli be able to produce that proton gradient, which will also let it involve an ATP synthase.